To end all that and realized I didn't give you the context of why we need to know anything about the atomic structure. And this is it. So we use the tungsten atom. Tungsten has an atomic number of 74, which means that it's got 74 protons. Its elemental symbol is W. It's got 74 protons, which means it should have 74 electrons. So it's got a relatively large nucleus. We use tungsten not just for the nucleus size, but for reasons that we'll talk about maybe in the next section. But it's got a relatively large nucleus. And you might be thinking, well, why does that matter? And it does matter because remember that the bulk of the mass is inside of the nucleus. The bulk of the elemental mass is inside the nucleus. Most of the space is empty. So what we're trying to accomplish whenever we create X-rays is we're firing something that's so small that it almost doesn't exist at something that is too small to see. And we're hoping to have a positive effect from that. We're hoping to create X-rays off of that. The likelihood that that's going to happen is extraordinarily low for an individual electron. What I mean by that is if our tungsten atom, our nucleus was that big, then our electrons would be so small we couldn't see them. And our first row of electrons, our innermost shell of electrons might be at the floor. So we're sending all these electrons across the tube, hoping to get them close enough to the nucleus of the atom to create X-ray photons. And it's just not going to happen easily. All right, so expanding that out, if we've got a nucleus that's that big and we send electrons across, it's still going to be very difficult to get a lot close enough to create X-rays. But if we have a larger nucleus, it's going to be easier. So what we're hoping to do is send electrons into the atom once we hit exposure, close enough to the nucleus of the atom to change the trajectory or the flight path of that electron. And if we do enough so, then we're going to kick off an X-ray photon equivalent to the energy that it came in with minus the energy it left with. So we're talking about difference, mathematical difference. Difference means subtraction. So anytime I draw an electron, it should be a straight line until it curves around the nucleus of the atom. X-ray photons are always going to be squiggly lines. All right, so electrons, projectile electrons. I think one of the PowerPoints might have said incident electrons. I'm going to use projectile electrons because we're throwing them just like a ball. We're throwing electrons at the nucleus of the atom. So if it gets close enough to the nucleus of the atom, it could create an X-ray photon. And that's what we refer to as brims. Brims is short for Bremsstrahlung, which is the German word for breaking or slowing down. So according to the Bushong book, 85% of our X-ray beam consists of Brem's X-rays, and the other 15% are characteristic. So characteristic X-rays occur when, this is nucleus of the atom, so I'm just going to put positive and neutral. Characteristic occurs whenever the X-ray, the incident, the projectile electron hits an orbital electron. So it hits an orbital electron, but it's got to have enough energy to knock that out in order to create a characteristic X-ray photon. So if we have an electron that's traveling in, carrying with it 80 kVp worth of energy, the binding energy, remember this from the recording, the binding energy of the inner shell electron is 69.5. Bushong book, in the chart says 70, but we're just going to say 69.5. That's what's most commonly used. 69.5, it's held in with 69.5 keV. That keV is an equivalent but different force from kVp. So it's the same amount of force, it's just different. All right, so 80 kVp will eject to 69.5 80 kVp will eject a 69.5 keV electron, and it will leave a vacancy here. And this is inner shell electron. That's not a stable condition for the atom to be in. So it's going to try to snag an electron to replace that one. If it comes from this next shell out, the L shell, that's being held in place with 12 keV, then it will fall into place and will kick off an X-ray photon equivalent to the difference between this and this. So 69.5 minus 12, we're just going to knock off the half. We're going to say 69. So that would be a 57 kVp X-ray photon. So looking back at that chart that I referenced earlier in the other video, if you look at the binding energies of the barium versus the tungsten, then the binding energies here and here are totally different, right? And that has to do with the proximity of those electrons to the nucleus of the atom and how big that nucleus of the atom is. The tungsten atom is bigger than the barium atom, and the electrons are closer to the nucleus of the atom. So, as characteristic of the tungsten atom, if we use barium for the target, and that's what this is the target of the X-ray tube. If we use barium for the tungsten, or for the target of the atom, then our characteristic X-rays would be something totally different. Characteristic means that it's characteristic of the tungsten atom. We change the atom that we use in our target material, and it'll be something totally different. So we eject the inner shell electron, replace it with something else, and we're going to create an X-ray photon equivalent to those two. The only characteristic that we tend to chart, I'm not real sure why, is if we eject an electron and we replace it with an electron that might have got knocked out of a different atom and it pops into place. So if that happens, then this electron, it's not a projectile electron, it's a free-floating electron. So if it snaps into place, then we're going to create an X-ray photon equivalent to, there is no binding energy on that, so 69.5 minus 0, 69.5. So we create characteristic X-ray photons in every possible interaction with any shell electron, but the only one that we keep track of is this interaction where we have ejection of the inner shell replaced with an unbound electron. So we say that the energy of our characteristic X-rays, and it's really the maximum energy. We create characteristic energies in a lot of different energy ranges, but it's going to be 69.5. We're going to talk about that in the next section whenever we go through X-ray creation, or the section after. We'll go through X-ray creation. We'll talk about all this again, but this is the context of why you need to understand the atomic structure. The bigger the nucleus, the more likely this is going to happen. Now, all of that being said, the likelihood that it will happen is very, very low. So, we can get rid of this. Again, you've got it recorded, so you can kind of back it up, look at it if you want to. But when we create X-rays, I've been through this several times, the main thing that we create is heat. And that is why, is because we've got this atom that is mainly empty space with this tiny little bitty nucleus that, even though it's tiny, it has most of the mass of the atom, which is empty space. And we're going to try to send electrons at that nucleus and hope that they get close enough to the nucleus to change directions, create a Brem's X-ray. And it's unlikely that it's going to happen. We're shooting something that's so small it almost doesn't exist at something that's so small we can't see it. And we're hoping to have a positive effect out of it. So what we use, of course, is KVP. That controls the speed with which the electrons travel across the tube. Once they become X-rays, they all travel at the speed of light. But that has no place here. Really, in the likelihood that we're going to create X-rays. But mass is milliamps, and amps is just a count of electrons. So with the amperage, what we're going to have is if we create a 1,000 mass exposure, we're using 1 amp. And an amp is 6.21 times 10 to the 18th power electrons. So what we've got, if we made this exposure, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So what we say about X-ray creation is it's very inefficient. So what we're going to do is we're going to throw a tremendous number of electrons at the patient. You're probably never going to make 1,000 mass exposure. All right, so if though we did make 1,000 mass exposure, we would be sending this many electrons across the X-ray tube. Surely some of those will get close enough to the nucleus of the atom to give us those Brim's X-rays. Surely some of those would hit some of those inner shell electrons and give us some characteristic X-rays, right? But we don't use that. So let's say though that we use a 1 mass exposure. All right. So if we were to divide that by 1,000, we don't have to put pen and paper to it. Pretty much all you got to do is knock 3 zeros off. We're still going to send that many electrons across the X-ray tube. But we say that X-ray creation's not efficient, and only about 1% of what we send across the tube become X-rays. So if we divide that by 100, because 1% would be 1/100, so if we divide that by 100, we're still sending that many electrons across the tube. And then if we say, well, most of those X-rays that we create are going to be low energy X-ray photons because, we're shooting things that almost don't exist at things we can't see and hoping they get close enough to the nucleus, and most of them won't. And you would be 100% right. But if only 1% of those were any good at all, we'd still have that many X-ray photons. That's a big number, right? So even though it's inefficient, just because of the number of electrons we're going to throw at the target, we're going to get a lot of X-ray photons. So I hope this helps you to understand why it is we need to understand the atomic structure and how that plays into the creation of X-rays, which we're going to talk about in the next section as well. I do want to show you a couple of things real quick. I've been promising to show these things to you in class. So what I've got here are 2 different things. I've got 2 different anodes, or targets really. This is an entire anode assembly off of a very old machine, but this is just the target area, the target disk off a newer machine. So whenever you hit your prep button, this is the thing part of the thing that goes from 0 to 3,000 RPM in a second. So you can see it's kind of scuffed up a little bit, but it's not all that bad. I don't really know what happened to this X-ray tube that they tore it apart. But this is an old, what we refer to as a stationary anode. And you can see what happens if you were to put a tremendous amount of exposures in a single spot. Eventually you'd melt the anode. So what this is it's primarily, it looks like copper or bronze, probably copper, probably with a small piece of tungsten over the top of it. So it eventually melted through the tungsten and just really had its way with the copper. So the reason we rotate it is to prevent that. The filaments, I told you I'd show you what the filament looked like, and this is harder than what it seems like it should be. But you see that what we've got in this thing, this whole thing is what we refer to as cathode. And I'll talk about the individual components of this, but this has got 2 different filaments, and the filaments are just like a light bulb. It's just real curly wire. So this is where we get the thermionic emissions and where we send the electrons. So we send them from this thing across the tube to hit the anode to create the X-rays. So this is a source of thermionic emissions. This is where we create our space charge before we send them across the tube. So when we hit our prep button, we spin the anode, we heat this thing up. All right. And then our X-ray tube itself, you can see the components of it. And we've got to be real careful with this one because it's already broken. It's got cracks in it. But you can see the individual components. So we've got the entire rotor assembly at this end of the X-ray tube. This entire thing, this black thing spins along with the disc that you see in there. So you see the distance between the cathode and the anode is not very far. So we create our thermionic emissions on this thing and we send them across the X-ray tube to interact on the face of the target. So I hope this clears up what I did not get to in the last recording, and I hope it gives you some sort of visual perspective of what I've been talking about and some of the components inside the X-ray tube. So if you would, just like the video, hit the thumbs up button, and if you're not one of my subscribers already, please hit the subscribe button as well. Thank you very much.